Hello, everyone. Welcome back. So this week is going to be short because, on Thursday is Thanksgiving. So um, you'll have a little bit of break and we'll meet back again on next Tuesday. For the exams, I have finished grading about um, almost 20 of them. So I expect to finish by today and then I'll upload the rest of the scores. Um, Then today on chapter 6 homework, we're going to finish chapter 6 today. So the homework will be due next Tuesday. So at the day you get back from the break. So I encourage you to work on the homework over the break just to keep your minds kind of familiar with this information, because there's going to be a lot of information that we're going to cover today. And we need to pick up the pace a bit, or I need to pick up the pace a bit. So we're going to go through the lecture slides pretty fast, but I encourage you to watch the lecture and have the slides open so you can take notes, because this chapter is really dense with lots of information to cover, especially about naming. So we're just going to jump right back into it. So today we're going to finish up chapter 6, which is nomenclature. So we haven't really talked about nomenclature yet, but here is the how we do nomenclature in chemistry. So for binary molecular compounds, you have either a nonmetal and a nonmetal, or a nonmetal and a metalloid, but usually it's a nonmetal and a nonmetal. So in this case, how we name nonmetal and a nonmetal in a molecular compound, binary molecular compounds, so compounds that consist of two elements. So we have prefixes that we use to indicate how many of a certain element is in the chemical formula. And then the second element is where we change the name of the element. So the first element, we keep the name, we may have a prefix. The second element, we may have a prefix. So usually in the second element, you always have a prefix, and the ending of the name changes. In the first element, you keep the standard element name, and you may have a prefix. If there's only one of that element, one atom of that element in the chemical formula, we do not include a prefix. So we're going to talk about some examples of this. So the ending for the second element, you would change the ending. For example, um, say I have xenon hexafluoride. So you see xenon, the name is the same, but for fluorine, I dropped the INE and added a IDE, so fluoride. So ide as in ride. So we changed the name of the second element and replace it with that ending. So there's certain elements that we keep the traditional names, like water and ammonia. So we would never call. You may have heard water be called like dihydrogen oxide or dihydrogen monoxide, but we do not usually refer to those names. We just simply call it water for H2O and ammonia for NH3, because traditionally that is what they're known as. And in everyday life, you always refer it to those two names. Okay. So these are the prefixes I expect you to know the use in naming. So mono, di, tri, up, all the way up to deca. So these are the prefixes that we will use to denote in binary molecular compounds how many atoms are present in the formula. Okay, so let's try some exercises. We are going to name these compounds and write the formula. So dinitrogen pentasulfide. So what you should keep in mind is these prefixes here: di, penta, di, and pent. And then you see here under second part is the name of the elements. So you see here the prefixes, they tell us how many of that element is in the formula, and we could translate it vice versa. So dinitrogen means we have two nitrogens. That's the first element, nitrogen. So nitrogen is actually spelled incorrectly. It's not nitrogen, sorry, it's nitrogen. So let's just erase that R here. Just cross it out. Sorry about that. Then penta means 5. And when we have penta in front of sulfur or the sulfide, that means we have 5 sulfur atoms in the chemical formula. So sulfide is the second element. So we add the IDE ending to the sulfur. So we drop the UR and we add the IDE. So what letters we drop is just to make sure the name sounds nice in a way. So it's easy to say, easy to remember, stuff like that. So the second one, dinitrogen. So that's N2 again. Then we have pentoxide. So you may be asking, why don't we have pentaoxide? Well, when we have 2 vowels close together like that, it's kind of not free flowing or it doesn't sound as it doesn't sound easy to say. So pentaoxide, that doesn't sound like easy to remember, but pentoxide, we could easily remember that. It sounds more crisp, more easy to remember. And so when we have 2 vowels like that, you're going to drop the vowel and just use the vowel in the element name. So pentoxide. So in that case, we have N2, so di is 2, pent is 5, so 5 oxygen atoms. Okay, then the last ones, we're going to translate it to the name. 4 iodine molecules, so tetra, 4 iodine, first element. Then we have 9 oxygens, so we're going to call it nonoxide. We do not call it nona-oxide because that sounds a little bit winding in sound. So we do not say, we drop the vowel of the nona and we put the A, we drop the A and we just keep nonoxide. Okay, now we have PF5. So remember what I said about prefixes? When you have 1 in the first element, it is not necessary. So we just say phosphorus, penta for 5 fluorines, pentafluoride. So you might be asking, so if we don't have to use mono for the first element, why do we use mono for the second element? Well, the second element actually matters because it differentiates between carbon monoxide versus carbon oxide, right? So if you say carbon oxide, that's ambiguous. It can refer to any of the oxides of carbon, carbon dioxide, carbon monoxide, or any other compound that may have carbon dioxide or carbon monoxide as part of the formula. So we need to be very specific. So for what we only use the prefixes to denote one element in the compound in the chemical formula for the second element, not for the first. So carbon, we usually don't say monocarbon monoxide, we say carbon monoxide. So the prefixes are absolutely essential. You must always put the prefixes for the second element. Okay, so here's our solutions here. We went over them. And if they do not make sense, I'm always happy to help. Okay, so we talked about ions last chapter. So here's a brief summary of them. So we're going to talk now about naming these ions. So this is just a brief summary. We went over it, but please glance over it if you need a review, especially after the midterm. I see some students are not sure what a positive negative ion is. So please review this slide. So how we write ions is we take the chemical symbol and then we put in the superscript. So the superscript is the top right corner, right? Or it could be, usually superscript is the top right corner, like how we write 2 squared, we put the 2 in the top right corner. So we represent charges the same way. So we put the element symbol, the letters, then put the number first, then the negative or positive charge. It does not matter, negative or positive charge. So that's the convention I want you to use. Of course, you can put the charge first or the number. I don't really care. I don't have a preference, but traditionally the convention is number first, then charge. Whatever method works fine. So for ions, so when we have a monatomic ion, so an ion that has only composed of 1 element, for example, bromide, sodium ion. So when we talk about cations, we simply write the name of the element and say ion. For example, sodium ion. We do not say sodalide ion. That doesn't sound right. So we only change the ending for anions. For example, chlorine, when we're talking about the chloride ion, when we're talking about the ion, we call it chloride. So we take the ione of chlorine, drop it, add IDE, and say chloride ion. So that's how we would, we'll talk about the charges. So we're going to have some practice with this now. Sorry about that. Okay, the names. Okay, so let's just clarify some things here. So this should be 2 plus. Sorry, that was a typo. I will fix these by the time the lecture is posted. I will update the slides. So sorry if the slides are not updated right now. So let's talk about the names of Br minus and Ba2 plus. So Br is for bromine. So remember, it's an anion. So anions, we write the element name, drop the ione, add IDE. So the name of Br minus is bromide ion. Barium is a cation, so we just write the name followed by ion after it. So here is barium ion. Now, what about the formulas for the potassium and fluoride ions? What are those formulas? So potassium is a cation, it's a metal, so it likes to form cations. So we call it potassium or K plus ion. Fluoride is like bromide, a halogen, likes to form anions and compounds. So we call it the F minus ion, because remember halogens, they have similar charges. So fluoride already have the same charge in their and respective compounds. So we have F minus. So here again, let's just annotate this. 2 plus, barium ion, then potassium and fluoride ions. So hopefully this gives some practice. You also have the homework to go over this and review and practice and get the hang of writing these names. Okay, so additionally, you have transition metals that can have 2 or more different monatomic ions that have different charges. So these are mostly referring to the transition metals or the elements in the 3D block. So notice that we didn't specify what charges these atoms have in the D block in the transition metal block, so that middle section of the periodic table. And that's because like the word transition, they tend to have different charges depending on what kind of compounds they form. So we can't really assign them one charge. So, but to distinguish them, we write the name of the element because it's a cation. We don't change the name. In parentheses, we put the charge of the ion. For example, iron 2 plus, we say iron parentheses Roman numeral 2 ion. So you should put it as Roman numeral. Do not put iron then the number 2 in it or spell out 2. That is incorrect, and that will get you marked off. So just put Roman numeral 2. If you need to remember the Roman numerals, it's okay. Just know up to like 5 or 7. You're okay. Because I don't think there'll ever be any charges greater than 7. I've never seen a charge of +8 or anything. The only charge I've seen of +7 is manganese, and manganese is known to have very, very, very different and a lot of different charges in its reactions. Okay, so that's iron 2. Iron 3, we represent as Fe3 plus, so we'll name it iron parentheses Roman numeral 3 ion. There's a special case for mercury, but I wouldn't pay too much attention to it. It's very rare, but it can pop up. So I will go over it in detail. So mercury, it does not, a single atom, a monatomic ion of mercury does not exist under normal conditions. It exists as this guy. So Hg, or this species. Hg2 So it's composed of a diatomic ion, Hg2 2 plus. So we name it as if each of the mercury atoms have a 1 plus charge, because we cannot observe Hg plus on its own under normal circumstances. So we call it the mercury 1 ion. It's not Hg plus, that's not mercury 1. It's Hg2 2 plus, with each mercury atom having a 1 plus charge. So that is the very special case. That's probably the only one you have to remember. Okay, let me take a water break. All this talking makes it dries out your throat. So anyway, so here we were talking about manganese earlier. So let's write the names of manganese. So Mn is manganese. So people confuse manganese with magnesium. Don't do that. A lot of people in the naming last year when they tried to name, they will often confuse manganese with magnesium. So remember, Mn is manganese, Mg is magnesium. So how do we name Mn2 plus and Nm3 plus? And how will we name nickel 2 ion and nickel 3 ion? So we're just going to use the parentheses to denote the number of the charge for our ion. So we have manganese 2 in parentheses ion, manganese 3 parentheses ion. Then for nickel, we know it's nickel 2 ion, so it's going to be nickel 2 plus and then nickel 3 plus ion. Okay, so now it gets a little more complicated. So there's certain ions that exist that are polyatomic. What that means is that they're composed of many atoms, and the group overall has a net charge. So for example, ammonium is one of the most common ones, ammonium, NH4 plus. So the whole unit has a plus charge. Do not worry where the plus charge exists, whether it exists on the hydrogen or the nitrogen. That's not important right now. But what is this saying is the nitrogen atom is chemically bonded to 4 hydrogen atoms. So the nitrogen has 4 hydrogens around it, bonded. And I'll tell you now, the plus charge is on the nitrogen. The hydroxide ion, another famous one, hydroxide is a very ubiquitous ion. So hydroxide, OH minus, oxygen and hydrogen atom are chemically bonded to another, and the charge is on oxygen. But do not worry about that right now, because it's not important here. So ammonium, positively charged, hydroxide, negatively charged. So like every ion, you could think of it as having a positive charge. Every IDE is a negative charge. Okay. So we talked about ionic compounds, and then we talked about that they're composed of positive and negative ions, and that the formula unit represents the chemical formula, or the smallest what we say collection of ions that are represented by that chemical formula. So we can't really say molecule of ionic compound, because that would make sense. They don't exist as a molecule. They're ions kind of held together by electrostatic forces, and not really a sharing of electrons. So that's why we call it formula unit. So we just call it like that's the smallest representation of an ionic compound. Okay, so to write ionic compounds, or writing the formula, or converting to names, we writing the name. So, but first we'll talk about writing the formula. So you have to think about the charges of the formulas. So so you need to think about the charges of the elements that make up the formula, and you need to combine them in a ratio in the chemical formula that balances the charge or has a net neutral charge of 0. So we can so the formula can be tinkered with, say, by changing the subscript number, denoting how many atoms there are for the for the ionic compound. So this is much different than the binary molecular compounds we were talking about earlier, because those numbers are unique for each type of compound. But for ionic, it's going to be for ionic compounds, they'll only have one possibility of ratio of cation to anion, and we'll talk about that. So if there's only one of each ion, for like one sodium, one chloride, we do not put the subscript 1, we omit it. So, and if we have a polyatomic ion like hydroxide or ammonium, we need, when we're putting subscripts to denote more than one of those ions in the formula, we need to put parentheses first, because it's a group of atoms, so we must multiply everything by that subscript. Okay, let's talk about, let's do some examples of how we show this. So let's write the formulas for ammonium bromide and ammonium sulfide. So we have here, so let's go back for this, sorry about that. So ammonium, remember ammonium is NH4 plus. So let's write that here, NH4 plus. Bromide is Br minus. And sulfide is S2 minus. So remember, sulfide, it likes to gain 2 electrons to complete an octet. So we say it has a charge of 2 minus. Okay, so now we know those representations. Ammonium bromide is -1, and ammonium is +1. So now they're balanced. So we could just write the chemical formula as NH4Br. We do not include charges because it's implied. And then ammonium sulfide, ammonium's +1, while sulfide is 2 minus. So to balance out the charge, we need to include 2 ammonium ions in the chemical formula. So it's going to be NH4, parentheses, subscript 2, S, S. So when you're writing these numbers, always write them as subscripts. Do not write them like as coefficients in front of the symbol. Write them as subscripts. Okay. Here's the formulas of the 3 ions, and then ammonium bromide, 1-to-1 ratio. They're both of the same magnitude of charge, so we only need 1 of each ion in the formula, like so, NH4Br. Then ammonium sulfide, we need 2 NH4 ions to counterbalance, or sorry, not counterbalance. I don't know, like I said that. I meant to balance the charge, and that's the S2 minus ion. All right, so we have 2, so NH4 parentheses 2, S. So remember, ionic compounds, you want to balance the charge. This does not apply to molecular compounds because they do not form ions, so the compounds we talked about earlier. Okay, so let's try this, aluminum oxide and barium nitride. So aluminum, remember, aluminum is Al3 plus. Sorry, that's a really horrendous looking 3. So aluminum 3 plus is, so remember, aluminum is still a metal, so we consider it a metal, and it's in the group 3A, so we lose 3 electrons. Aluminum loses 3 electrons. So oxide, remember, oxide is oxygen, so oxygen is like sulfur. It likes to gain 2 electrons to complete an octet. Barium we talked about earlier, 2 plus, and then nitride is nitrogen. Remember, nitrogen has 5 valence electrons, so we subtract that from the octet rule. It wants to gain 3 electrons to reach the octet, so 3 minus is right here. So nitride is 3 minus. Okay, so this example is where we get into kind of tricky territory, because there are 2 different charges. So how do we write a formula if the charges are so different? Well, we have to find the common factor of them. So common factor of 3 and 2 is 6. So we multiply oxygen by 3 and then aluminum by 2. We'll get a balance of charge. But another way to think about it is to use something called the crisscross rule, which I do here, aluminum right here, oxygen right here. So then I say the 2 is going to go to my aluminum as my subscript, and the 3 is going to go to my subscript for oxygen. So we get Al2O3. So you use the crisscross rule like that. Well, it should be like it should be like this. Sorry, crisscross. So it's sort of like crossing lines. Sorry if that's messy. So here's a better example. So barium, we could use the same idea. So we have barium 3 and then nitrogen 2. So the crisscross rule is helpful if you do not like doing mental math, but mental math is a good check to see that it's correct. So we our solution here is Al3. Sorry, I can't. So here we go. Let me just reload that. Aluminum 3 plus and oxygen 2 minus. So we use the crisscross rule, or we just know that the common factor is 6. So you just want to use the least common factor, and we see that the charges here will balance out. That is our formula here. Al2O3. So use the crisscross rule. I think that's a very helpful way to look at things if you do not want to do the mental math. But just know that the charges need to be neutral or 0. So barium nitride, same thing. It's just the opposite. Now the cation has the lower charge or the lower value of the charge, and the nickel. So this should not be nickel. I apologize. That should be N. So this should be N. So sorry about that. So now we have balance of charge, and we have barium 3, N, not Ni. Sorry about that. Nitrogen. So nitride. So I'll make sure these typos get fixed. Okay. So for when we name ionic compounds, we do not use prefixes at all because it only involves the name of the cation and anion, and there's only a certain ratio for a specific ionic compound that will be unambiguous. Sorry. So you don't need to say prefixes because there's no other way you could name the ionic compound, because it only depends on the number of ions in the compound, and it's very unique for each type. However, if you do have a transition metal, you need to specify its charge. For example, iron 3 chloride versus iron 2 chloride. So if you just say iron chloride, that is ambiguous, and we do not know if you're talking about iron 2 chloride. So we don't know if you're talking about FeCl3 or FeCl2. So there's a problem there. However, when you talk about something like magnesium chloride, there's only one formula that fits, and that's MgCl2, based on the balance of ionic charge. Okay. All right. So let's write the names of these elements. So first one, lithium, then Br, bromide, lithium bromide. So we just use the first name of the element, the second name of the anion or the element, drop the IDE. So lithium bromide. Remember, don't call it lithium monobromide because these are ionic compounds. So ionic compounds don't need prefixes. Magnesium, MgI2, magnesium, I2, iodide. Then, all right, this one is silver is kind of not considered transition metal, even though it's in the area of the periodic table. And that's because it only usually has one charge, and that's +1. So we could just call this silver nitride. So silver nitride. So the main confusion is people use prefixes even though we specify not to. So remember, ionic compounds don't use prefixes. We will mark you off for that. So do not do that because it's technically wrong. It's okay. It's technically not wrong, but it's unnecessary. You don't need to do that. So unless you need to absolutely do that to differentiate it from something else, you you should do that. But for ionic compounds, you do not need to specify prefixes. So it's not necessary. Now we have MnCl2. First element is manganese. So, but what charge is the manganese? Because you can't say manganese chloride because that's an unambiguous name. So, sorry, that's an ambiguous name, so that won't work. So for manganese, we need to say, so we know chloride is -1, and we have two of them. So we have a total anion charge of 2 minus. So to balance that out, manganese must be 2 plus. So we have manganese 2 chloride right here. Okay. Give me 1 second. Okay. So now we're going to talk about acids. So acids are substances that yields hydronium ions, or basically protonated water. So hydronium ion is formed from the reaction of water um, reacting to form a bond with a proton that is formed in solution. For example, when I bubble in hydrogen chloride gas, it forms an acid called hydrochloric acid, and it donates a proton very readily to solution, and the water picks it up to form the hydronium ion H3O plus. And that's because hydrochloric acid is one of the strongest acids in existence. And it's used for, it's very useful. But anyway, so the hydronium ion forms by this reaction right here. But do not worry about the reaction for now. We're just going to talk about naming acids. So this is just like an introduction. Okay, so we're going to talk now about acids, of the variety of them. There's a many acids. So if there's acid formulas you should know, it's these that you should memorize. And then we're going to relate these acids to the other kinds of acids based on their similarity in chemical formula and structure. So carbonic acid, H2CO3, carbonic acid is what happens when you absorb CO2 from the atmosphere, and in your blood, it forms carbonic acid. Nitric acid, one of the strongest acids. Phosphoric acid. Phosphoric acid is used in the food industry, very prevalent. So that's something that you probably have seen somewhere, in your daily life. Sulfuric acid, one of the strongest acids. I mean, it's used in car batteries to produce electricity and power your engine. So very, very, very useful. It's also very used in reactions in chemistry. Chloric acid. Chloric acid has some, I think, not so common applications, and you really don't see it. If you ever read literature or like in synthetic uses, I don't think chloric acid has much use. And you probably just learn it in general chemistry. That's where I learned it, and I haven't really heard of it since. But chloric acid is a good reference acid to refer to the other acids that are similar. So we'll be talking about that. Okay, acids. So acids has they have proton, what we call acidic protons, so hydrogen atoms, so variable number of hydrogen atoms. They're associated, or the formula has a non-metal atom, and then usually a variable number of oxygen atom, and that's where the hydrogens are attached usually. So oxy acids, they contain at least one hydrogen that can be removed by water. If we dump in the acid in water, it'll be removed to form an acidic solution. And it usually has oxygen. Oxy acid refers to the oxygen, usually oxygen, and one other type of atom. So there's halogen families. They have oxo acids. So remember chloric acid, the one I want you to remember. Then there's other chemical families like sulfur, selenium, tellurium, and phosphorus and arsenic acids that are common. So I would refer back to those of the acids that you'll have to be able to name, but we're going to go over it. But be aware, it's a lot. So there's going to be a prefix and suffix system that we can show the relationship between the name and the chemical formula, and between specific prefixes and its relationship based on the formula to other prefix and suffixes. Okay. So say that we know that H2SO3 is sulfurous acid. So what is the name of H2TiO3? Remember, tellurium, if we look here, tellurium is in the same family as sulfur. See tellurium right here. Tellurium is in the same family as selenium and sulfur. So we can use that to predict the name for this compound. So since H2SO3, O3, so the same number of oxygen atoms for this guy, H2TiO3, or this species, so how will we name that? Well, we would just take the IUM off and add OUS. So it's called tellurous acid. So notice that sulfurous, we just add OUS. For tellurium, we take off the ending and add OUS. So it has the same us or rus sound, your rus sound. So that will be tellurous acid. So we changed the name of the first of the, of the central element. And then we add the suffix ending and OUS to the end to find our acid name. Okay, given that the formula of perchloric acid is HClO4, so notice that chloric is HClO3, so it's one oxygen above the name. So we have HClO4, that's perchloric acid. So what would be form of perbromic acid? Well, chlorine and bromine are halogens, so they're in the same family, so they'll have the same similar formula. So we just substitute bromine for chlorine in the formula, and we get our formula for perbromic acid. So it follows that model set for perchloric acid for group 5A. So we can see that if we go back here, right here, bromic. So we'll talk about why it's per and ic in a minute, but it follows that same formula that if we have chloric acid and then bromic acid, then if we have perchloric acid, we should have perbromic acid. Okay, so the reference name you want to use is the chloric acid. So those acids I mentioned earlier in that table, those are the ones you want to memorize, and then you can relate back how the other acids similar in structure are named. So if we have one more oxygen, we just went over that. We have the prefix per and then ic at the end, so that's like perchloric acid. One fewer, so HClO2, we now have the OUS ending, so we call it chlorous acid. So there's no prefix, there's only a suffix, and it's OUS. Now, when we have two fewer, we have HCl1 oxygen. Now that's called hypo. So hypo is like very few oxygens of the series, so the lowest it can have, so 1. So then we have hypo as the prefix, then the suffix is OUS. So I know there's a lot to remember and memorize here, but it's easier if you kind of look at the reference acid, which is the IC acid. So those reference acids, so you can kind of relate back how the naming changes according to the formula. And now with no oxygens, we just have hydro and then IC at the end. So hydro is the acid prefix, and IC is the suffix. So think of hydro like you only have hydrogen in there, so it's hydro, no oxygen. But when you get to oxygen in there, now you have either hypo, us, per, ic, or ic acids. So use this chart to kind of compare and refer back to how we should name the acids. Okay, so I know that's a lot to take in, but please stick with me. Okay, so what's the name of H2SO3? So remember, our baseline, we want to refer back to H2SO4. So that's sulfuric acid. And then remember, this is one oxygen less. So one less O. So that will give us our OUS ending. And then the slides will go over this. So we have ic acid, so memorize sulfuric acid. Those one acids I want you to memorize. Then we see it has one fewer oxygen than the ic name, than the ic acid. So we call that sulfurous acid. Okay, so how about tellurous acid? Well, tellurium is the same group as sulfur, and it comes from tellurium. So it's the same family as sulfur, right? So it looks like sulfuric acid, except the S is a TE. It has one less. The US refers to one fewer oxygen atom, so this should be OUS. Sorry about that. And so it's the same kind of name. So we have the same ending, OUS, for tellurous acid. Okay, so hopefully it's not too intimidating. This chapter causes a lot of headache for most students, so it's important that you spend a lot of time honing your nomenclature skills here. Okay, so now we have to talk about another type of naming, and that has to do with the ions that we form. So when we have an oxoanion, that means we have it's an anion that's formed by the removal of a hydrogen or proton from an acid, and that's what we call an oxoanion. For example, we have chloric. So this is another typo. Sorry, guys. It should be a 3 right there, not for 3 chlorines. So it's HClO3. So remove the hydrogen. So every time you remove a hydrogen atom from an acid, you're going to remove a positive charge. So therefore, the resulting anion will be that charge based on the negative charge will be based on how many hydrogens we removed. So if we remove one hydrogen here, the ClO3 anion will be -1. So to expand on that, we have H2SO4, and we remove 2 hydrogens to form the SO4 2- anion. We have a charge now of 2- because we removed 2 hydrogens, or 2 H+ ions. So when we remove these ions are considered like ionic compounds because the hydrogen has a plus charge. So that's we refer to the H+ as a proton because remember, hydrogen has 1 electron and 1 proton, but no neutrons. So once we remove an electron, it's simply a proton. So that's why we call it a proton. Okay. This table, a lot of information, so let's go through it. So remember our memorized ic acid, hydrochloric acid. So now our anion, if it has the ic ending, just the ic ending, we call it 8. But if it also has the per and ic ending, the per prefix and the ic ending, we also call it 8. Or the ending is 8. The anion suffix is 8. So for example, ic, we'll have chlorate ion. When we have per ic acid, we have the per 8 ion, so per chlorate ion. So now when we have one fewer O2, that's the OUS ending, and we represent that anion ending by ITE, so chlorite ion. When we have 2 fewer, so only 1 oxygen atom, we the prefix is hypo, and the acid suffix is us. Our suffix for the anion is still ITE, but we just for like per chlorite ion, we have to keep the hypo, so we call it hypochlorite ion. And for stuff like HCl, when it's solution, we consider it like an ion. So we say hydrochloric acid. It has the hydro and ic, but we do not call it hydrochloride ion because there's no hydrogen there. We just call it the chloride ion as we usually see in ionic compounds. So our regular naming of binary molecular compounds. So we just no prefix and we just keep the IDE, so chloride ion. So that should be familiar, as we covered before in the previous slides. Okay, so let's move on. So let's try this. What is the name of NO2 minus? So our NO2 minus is nit. So where does NO2 minus come from? Let's talk about that. So remember, the memorized ick for nitrogen is nitric acid, HNO3. HNO2 has one less oxygen, so we're going to call it with the OUS ending for the acid name. So this would be nitrous acid with its hydrogen still attached. But since we do not have the hydrogen there anymore, we remember the OUS ending has the ITE ending, so we call it nitrite ion. We don't call it hyponitrite. That doesn't count. It's not two more oxygens removed. It's only one oxygen removed. So we have OUS ending nitrite. So this is the nitrite ion, like so. Okay, now about hypoiodine. So hypo, we'll talk about like which elements should have the hypo and per in their names. There's only a few, so there's only a few you have to remember, thankfully. But for hypo, remember it's our classic example is the chloride example, right? Not chloride, sorry, chloric acid, or HCl, HClO3. So remember, hypo has two less oxygens, so it's going to be hypo as the prefix, and then us for the acid name. So its prefix has two fewer oxygen atoms. So HIO is hypoiodous acid. So then for forming the ion, we remove the H, so it has a negative charge, IO minus charge. So that's the hypodite ion, because we have two oxygens removed from, for example, the reference name that I told you to memorize, chloric acid, bromic acid, iodic acid. So those are the reference ones you should be referring to. So if this is not making much sense, I understand this is a very difficult topic. But when you do the homework and you review, this should all be more familiar, and hopefully I will always recommend making flashcards for remembering nomenclature. That's the easiest way, I think, to do it. And also doing practice. Okay, so here are some of the ions that form by complete dissociation or separation of the ions in the acid. So carbonate loses two protons, forms carbonate ion, nitric, nitrate ion, nitrous, nitrite, phosphorus, phosphate, etc. So you also have sulfur. Then fluorine only has two kind of acids, hydrofluoric and hypofluorous. There's no per, ic, or us acid, only the last two. But iodine, chlorine, and bromine, they all have these five similar acid formulas. So just remember the endings related back to how many oxygen atoms are associated in the chemical formula. But now we must extend it to more atoms or more elements in the same families. For example, arsenic in the phosphorus family, like we saw here, phosphorus in the phosphorus family. We have arsenic, so arsenate, H2SO4, like phosphoric, arsenate, 8th ion. So the endings actually depend, the name of the endings or the name of the acids actually depend on what element is part of the acid. For example, is it a halogen associated with the oxygen atoms, or is it nitrogen or oxygen, sulfur, selenium? For example, selenite here is very similar to the sulfate example. sulfuric acid, selenate, selenite, and selenide for the sulfur example. We go back to the sulfur right here. Sulfuric, sulfurous, and hydrosulfuric. Very same for selenium, tellurium as well. So those are very similar to the sulfur example. So just remember the sulfuric acid, and then you can work your way backwards for any of those other names or acid names, and also different acids, for example, selenium and tellurium, because they're very similar. Now we get with the halogens. Bromine and iodine and chlorine are the only ones that form 5 different kinds of acids based on how many oxygen atoms there are. And they're very similar in naming and pattern. So try to get a hang of those, writing the acid names, writing the formula for the acid, and also forming the names of the oxoanions or anions in general of the acid when it donates protons to an aqueous or in water. So when it forms aqueous solutions, the proton it donates will form these ions from the acids. Okay, so this will take a lot of practice, and the homework will get you thinking about this. Okay, so let's write the name of this species. So Mg is magnesium, and we know BrO4. Remember, Ik is O3 for the halogens, so O4 must be one step above, so that's perbromic. So this comes from perbromic acid. We remove one of the hydrogens right here from perbromic acid, we get perbromate ion right here, and we see that it's BrO4 minus. So that means we have a 2 minus charge for the anion in the chemical formula. So magnesium will balance that out because magnesium only has 1 charge. So we call this magnesium bromate. Oh, sorry, not bromate. Excuse me, perbromate. Remember, we had perbromic acid. My apologies. Perbromate. All right, so magnesium perbromate. So potassium selenite. Remember, selenite comes from right here. Selenite comes from selenous acid, so H2SCO3, and that selenite, that is what. So when the anion, the oxoanion is selenite ion, so it's SeO3 2 minus because we removed 2 protons, or 2 hydrogen atoms from the acid. So the formula would be, so since selenite is 2 minus, we need to have potassium, which has a +1 charge, so we need 2 potassium atoms in the formula. So it's K2SeO3 because selenite is from selenous acid, which is SeO3. Okay. So there's also, you can also form compounds with like acid anions. So ions that have multiple hydrogens in the acid formula, and that can dissociate one by one to form individual ions. For example, for phosphate, you could lose 1 hydrogen to form the dihydrogen phosphate ion, then another to form the hydrogen phosphate ion. See, as we remove a hydrogen, the charge increases because we have to balance the charge as every time a proton is lost. So eventually we get to the phosphate anion, which is PO4 3 minus. So this can occur for any acid that has more than 1 hydrogen in its formula. So sulfuric and phosphate are the common examples, and other elements related to that: tellurium with tellurium, selenium, arsenic in the case of we're the same group as phosphorus. Okay, so these are some names derived. So some of the common oxoanions that have that have some of the acids that have more than 1 oxoanion possible or present, that can be present in in compounds, ionic compounds. For example, carbonate. So carbonic acid, the first acid on this table, it can form bicarbonate ion or hydrogen carbonate. So either of those names are fine. HS minus, hydrogen sulfide, hydrogen sulfate, hydrogen sulfite for HSO3, then dihydrogen phosphate, then hydrogen phosphate for the acids related or coming from phosphoric acid. So it's possible that these names might come up. So you can use either the preferred name or the other name for these ions. So what is the name of FeHCO3 subscript 3? So remember, iron has variable ion charge. So we need to first refer back to the what this is called hydrogen carbonate or bicarbonate ion. So remember, hydrogen carbonate comes from the carbonate ion. So we know it comes from the carbonate ion, which comes from carbonic acid. So there's a typo. It should say adding a hydrogen atom or adding an H plus to carbonate ion yields HCO3 minus. So once we add the H plus, the charge now turns to HCO3 minus because we combine them into this ion. So there's 3 of them, 3 of these -1 hydrogen carbonate ions. So the charge is total 3 minus for the anion. So the iron must be a positive 3 plus. So we could say it's iron 3 ion. So the full name is iron 3 hydrogen carbonate, or you could say iron 3 bicarbonate. That is also valid name. Okay, what about ammonium hydrogen phosphate? So remember, hydrogen phosphate is this group right here. So it's HPO4 2 minus, so the entry on the bottom. So we also call it dibasic phosphate because it has 2 minus. Because these compounds, phosphates are basic, so they're decent bases in base strength. So that's HPO4 2 minus. So now, how would we write this name? So hydrogen phosphate is HPO4 2 minus. So that's a 2 minus charge. Remember, ammonium is NH4 plus. So we have a 1 charge. So so we will walk this through, right? Phosphate is 3 minus. We would get adding an H yields HPO4 2 minus. So the 2 minus charge for hydrogen phosphate. So ammonium, we must have two ammonium ions to balance the charge from the hydrogen phosphate. So 2 ammonium ions will balance, and therefore we say it's NH4 parentheses 2 HPO4. So ammonium hydrogen phosphate. All right, we are not going over hydrates, so we're going to skip this section. So you're not responsible for it. Okay, so here's a summary of basically the nomenclature we talked about and of the formulas for diatomic atoms and elements. So review this slide for a brief overview of a summary of how we name these things. So go through the slides and just look at this review, and it'll tell you basically everything you ought to know. So, and the naming conventions and how we name things. So remember, I want you guys to memorize these acids because it'll tell you how to name and write the formulas for other acids related in the series based on the chemical formula and based on how many oxygen atoms there are. And these rules right here will get you thinking about how to think of the name and not necessarily memorize it per se, but flashcards will help. And but that doesn't work. Flashcards will definitely help. Okay, so that is chapter 6. Don't worry about hydrates. We're not going to talk about hydrates, so you don't need to worry about naming hydrates. because on the list of topics, it was one that was not necessary. It's not necessary to cover, so don't worry about hydrates because there's so many other names you guys will have, or everyone will have to um, be responsible for on the final, or on the second quiz. So it's omitting that is, I think, helpful for you guys, for everyone. Sorry. So if okay, so now we're going to talk about chat. We're going to go into the next chapter. So we have 20 minutes left. So we're going to switch gears into chapter 13, and now we're going to talk about drawing structures of compounds. Okay. So chapter 13 is right here. So let's open that. Chapter 13. So last time I recorded my computer completely died all of a sudden and restarted. So I had to re-record. So it looks like everything's working now. So let's talk about chapter 13. All right. So chapter 13 is structure and shape. So we're going to talk about the shapes of compounds and what they look like based on their chemical bonding. Okay, so when we talk about structure and shape, this is purely for molecular compounds. So compounds with two nonmetals, or a nonmetal and a metalloid. But the second one is we may encounter some of those. Okay. So learn objectives, we're going to draw Lewis diagrams. So we're going to explain what those are and talk about the molecular geometry around that atom. So stuff like this and electron pair geometry. This is called Vesper theory, where we're going to go into that. Okay. So when we're drawing a Lewis diagram, there's some steps you need to know. So you need to count the total number of valence electrons for the formula. We'll go over what that means. Then usually when you're drawing these structures, the least electronegative atom is in the center of your diagram. And then once we draw like a skeletal blueprint of where the atoms go, we connect the atoms with bonds, and then we fill the rest of the valence electrons with lone pairs and make sure that each atom of the structure, each atom that composes the structure has an octet around each atom. Because remember, octet is the most stable configuration for atoms in compounds. Okay. So one way to think about calculating, like say you have a tentative diagram and you have the actual diagram. So say you have the okay, so say you have we'll talk about this, but what it means is that you're going to have a formula, and then you're going to have you want to calculate, like, what if every atom had an octet or had a full shell of electrons. You will calculate that number. Then you will look at the actual chemical formula and calculate how many valence electrons there actually are, and then you will compare the two. And then you're going to say, oh, do we remove or do we subtract bonds from electrons? Sorry, not electrons from bonds and make them lone pairs, or make lone pairs into bonds. But we'll talk about that. So the Lewis diagram, you should check a few things. Hydrogen atoms can only have one bond. And so in every Lewis diagram, you're going to have a hydrogen atom always bonded. It cannot exist as a lone pair because it can only form one bond, and it's always going to be bonded to an atom. So it can never be a lone pair. But all other atoms should have at least 4 electron pairs. There's some atoms that may have more than 4, but we're not going to go, we'll touch on that later. All right, so let's draw the Lewis diagram for ammonia. So if we calculate the diagram, we calculate the valence electrons we get. So remember, nitrogen has 5 and hydrogen has 1. But we have 3 of them, so we have to multiply that by 3. So we get 5 plus 3 is 8 valence electrons. So remember, hydrogen is never central because it can only form 1 bond. So nitrogen is our central atom. Even though hydrogen is least electronegative, in this case, hydrogen can never be a central atom. So we say nitrogen is the central atom. Like so. See here, we have 2 electrons, 2 electrons, 2 electrons, 2 electrons. So we count those up. That is 8 valence electrons. So if you're not sure how many bonds there are supposed to be, you could do this. So we calculate how many valence electrons there are in the formula, but if we calculate, remember nitrogen wants 8 electrons and hydrogen wants 2 electrons. So that's 2 times 3 for the 3 hydrogens. So we get, equals. So we get 14 electrons. So this is ideal. So we take these electrons, 14 minus 8. So 14 is the ideal. So these are so this is how many electrons nitrogen wants ideally in a compound, and hydrogen wants 2 electrons. So we take the ideal minus the actual number of valence electrons in the structure, we can find out how many electrons should be in bonds. So 14 minus 8 is 6. Remember, there are 2 electrons per bond, per chemical bond. So we divide that by 2, and we get 3 bonds. So our ideal structure should have 3 bonds in it. And the only way we can have 3 bonds is if nitrogen is bonded to 3 hydrogen atoms, like so. And that's why we get our ideal structure here. So that is a tip I suggest you use because it'll save you time of where to connect the atoms. But usually you can use process of elimination to figure out the final structure. Okay, let's just zoom out of this and reload it so I can show you the other piece of writing. So 8 electrons. So yeah. So we match the tentative diagram. Tentative diagram match the electrons available. So it's basically saying that this drawing matches our calculated valence electrons that are available. So it's a good check. Okay, so the hydrogen carbonate ion is a little bit more complicated. So you should calculate the valence electrons. So remember, H negative charge means you're going to add an electron to the total count. And if you have a positive charge, you're going to subtract whatever the value of the charge is because it's a positive charge and you're lacking electrons. So we have 1H plus 4C plus 3 times 6 for valence electrons for oxygen and plus 1 for the charge. That's 24 electrons total of our valence electrons. We only count valence electrons because those are the ones used in bonding. So what we have here is for valence electrons, just remember the group number. Hydrogen is 1, carbon is group 4, oxygen is group 6. That'll tell you how many valence electrons there are. Okay, so hydrogen, there's no hydrogen. Well, there's a hydrogen, but it can't be the central atom, so it's the least electronegative element, which is carbon as the central atom. Least electronegative element, it forms like the hub that wants to share electrons. So then the oxygen and hydrogens are going to be connected to on the the sides of the structure. So this is one way to draw it. So if we use our, so we'll just go through this, then use our strategy to figure out how many bonds there should be. So you have 4 bonds. Okay. So we count the electrons, we have 2. So 2 electrons, 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 2 electrons. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So that is too many electrons. So we need to figure out how to so this is right now 26 electrons. So you see here that it does not match our calculated valence electron count above. So this structure is not correct. So we need to figure out how to kind of move electrons a bit. So one thing you could do to reduce electron count is take a lone pair and convert it to another bond. So this is what we do here. So what we can do is say we remove the lone pair from the carbon atom, right? So here's the carbon atom, the lone pair right there. So the lone pair on the carbon atom, we're going to remove that and then take one of the lone pairs from the oxygen atom and convert it to another bond between carbon and oxygen. So this idea right here is very tricky to understand because it's the first time we're going to talk about forming double bonds. So you can form double bonds between carbon and oxygen as long as it doesn't violate the octet rule. And we see here that for carbon we have 2, 4, and the double bond counts as 4 electrons, so that's 8. And then we look at the oxygen, we have 2, 4, then 4 again for the double bond, so that's 8 electrons around oxygen as well. So every atom that participates in the covalent bond, they share the electrons. So but we count both electrons for both atoms because they're sharing the electrons. Excuse me. So that was how we would go about solving this structure. One thing you can also do is, so we calculate, so we just calculate the ideal number of electrons. So hydrogen, 2, oxygen, 8 times 3, then carbon, 8. Because remember, carbon and oxygen, they want octets. So we have 24, 8 times 3 is 24, then 8, 32, 34 electrons. So if we subtract 34 electrons minus our 24 electrons, we get 10 electrons. Then we divide it by 2 to figure out how many bonds our structure should have. So we have 5 bonds. So see here that our structure has 1, 2, 3, 4, 5 bonds. So our ideal structure should have 5 bonds, as opposed to the other structure, which only had 4 bonds. So we could actually predict the structure if we use this equation here. So if we take the ideal number of electrons subtracted from the calculated, or the electrons calculated from the formula, we can figure out how many of those electrons should be bonds by dividing the result by 2. So that is a strategy I encourage you to do. And remember, you can only put double bonds between atoms other than hydrogen. So you cannot put the double bond between the oxygen and hydrogen. That hydrogen can only form 1 bond. You are not allowed to do that, and that is impossible. So do not do that. Form the double bond between one of the oxygen atoms. That'll be a valid answer. Okay, so let's now talk about. So you notice that it's we didn't talk about the charges, so we're not going to worry about the charges yet. So we'll talk about formal charges in a bit, or the charges on the compound. So where's the negative charge? So we'll talk about where that is in a bit. So let's just zoom out again. So all these the structure checks out, so we are good to go. Okay, so you do not need to worry where the charge is, but just know that the charge is somewhere. We'll talk about where it is in later, I think later in the lecture, but do not worry right now where the charge is. Just remember, when you have an ion, just enclose the structure in a bracket and put a negative charge on the as a subscript, a superscript. Okay. So we need to talk about resin structures. So resin structures are basically two or more equivalent structures. So for example, let's just go back for this case. So if I look at this case right here, I could put the double bond between any of the two oxygen atoms. Like right here, for example, or I could do it like right here. Like so. So that ambiguity means that the true structure for carbonate cannot be represented by just one of these structures. It's actually a hybrid of all of them. So in any given, it's an average of all three. It's kind of like genetics. The true you yourself are a mix between your mother and your father's genes. So it's kind of the same principle here, that what your appearance or your makeup is actually a contribution of all of everything that makes up the structure or makes up you. So this is the same thing for resonance structures. So resonance structures are the individual Lewis structures that satisfy a chemical formula for a compound. The resonance hybrid is the true picture. So it's like the average of all of those structures. Okay. Isomers, so isomers are like what we talk about, like isoelectronic electron configurations. Isomers are two compounds that have the same formula, molecular formula, but in actuality, their structures are different. So there's their connectivities. So how the bonds are arranged in the structure is different. But they do have the same number of atoms in the chemical formula. And usually they have different physical and chemical properties, these isomers. So they do have the same formula, but they are different in terms of identity. Okay. All right, so we have 1 minute, so we're going to end on this slide. So electron pair geometry. So when we arrange those electron pairs around the atoms, that's called electron pair geometry. So the structure of the structure of the electron pairs, or sorry, not the structure of electron pairs, but the structure of we can classify what these structures look like based on how many electron pair groups are around the central element, so the atom in the center. And that's called valence shell electron pair repulsion theory, because the electron pairs, they tend to want to adopt a shape that avoids electron repulsion between lone pairs on atoms. and electron bonding pairs between different electron bonding pairs to different atoms. So that repulsion gives our distinct shapes for these molecules. So they tend to want to be far away as possible. And that is represented by the electron pair angle. So electron pair angle is that angle between any two electron groups. It could be electron bonds, lone pairs, any two electron pairs. So electron pairs are bonding electrons, and the lone pairs around the atoms. So it's that angle formed by those and the central atom. So the central atom is always part of that angle. So it could be a bonding pair of electrons, or it can be, a lone pair and a bonding pair interacting. So it's that angle. And we'll talk about what those angles look like next time after we get back from the break. So the most common shape, or what we call the generic shape that all central atoms tend to adopt, or the most common, is tetrahedron. So for our purposes, we'll talk mostly about the tetrahedron, or a central atom that has four electron pairs or electron groups around it. So it'll take the shape of a tetrahedron. It'll want to adopt that shape. So we'll talk more about that and what these shapes are next time. So everyone, that is it. Hopefully it wasn't blazingly fast, but we know we had to pick up the pace. So we must go fast, because there's still some stuff to cover for the final, and this will prepare you for Gen Chem 2A and the 2 series in general. So everyone, that is it. Short week. So enjoy the little break. Have a great Thanksgiving. Celebrate with your immediate families. Be safe out there, and I'll see you. I'll see you next week, and we'll pick up where we left off in chapter 13. All right, bye.